They help in representing and calculating impedance, voltage, and current. The use of complex numbers simplifies the analysis of circuits with resistors, capacitors, and inductors by combining them into a single complex impedance. 2. Signal processing. In signal processing, complex numbers are used to represent and manipulate signals. Fourier transforms, which convert signals from the time domain to the frequency domain, rely heavily on complex numbers. This is crucial for applications like audio and image processing, telecommunications, and more. 3. Quantum mechanics. Quantum mechanics, the branch of physics that deals with the behavior of particles at the atomic and subatomic levels, uses complex numbers to describe the state of a system. The wave functions, which describe the probabilities of a particle's position and momentum, are complex-valued functions. 4. Control systems. In control systems engineering, complex numbers are used to analyze and design systems that maintain desired outputs despite changes in inputs. The stability and response of these systems can be studied using complex numbers, particularly through the use of transfer functions and frequency response analysis. 5. Fluid dynamics. Complex numbers are used in fluid dynamics to solve problems involving potential flow. They help in modeling the flow of incompressible fluids and analyzing the behavior of fluid around objects. 6. Electromagnetism. In electromagnetism, complex numbers are used to describe electromagnetic waves and fields. Maxwell's equations, which govern the behavior of electric and magnetic fields, often involve complex numbers to simplify the calculations of wave propagation and interactions. 7. Fractals and chaos theory. Complex numbers are fundamental in the study of fractals, such as the Mandelbrot set. These mathematical structures exhibit self-similarity and are used to model natural phenomena like coastlines, mountains, and clouds. Chaos theory, which deals with dynamic systems that are highly sensitive to initial conditions, also relies on complex numbers. 8. Computer graphics. In computer graphics, complex numbers are used to perform transformations and rotations. They help in rendering images, animations, and simulations by simplifying the mathematical operations involved in manipulating objects in a virtual space. 9. Mathematics and calculus. Complex numbers are used in various areas of mathematics, including calculus and differential equations. They help in solving integrals, evaluating limits, and finding solutions to polynomial equations that do not have real roots. 10. Cryptography. Complex numbers play a role in certain cryptographic algorithms, which are used to secure communication and data. They help in creating complex encryption schemes that are difficult to break. Summary. Imaginary and complex numbers are not just theoretical constructs, they are powerful tools that simplify and solve real-world problems across multiple disciplines. Their applications range from engineering and physics to computer science and beyond, making them indispensable in both academic and practical contexts. If you have any specific application you're curious about or need more details on, feel free to ask. Complex numbers are quite useful in fluid dynamics, particularly in the study of potential flow, which is the flow of an incompressible and irrotational fluid. Here's a detailed explanation with an example. Complex potential and velocity. In fluid dynamics, the complex potential F(z) is a function used to describe the flow of a fluid. It combines the velocity potential \phi and the stream function \psi into a single complex function, where z equals x plus I is a complex variable representing the position in the flow field. Example, flow around a cylinder. Consider the flow around a circular cylinder. This is a classic problem in fluid dynamics where the complex potential can be used to simplify the analysis. Complex potential for uniform flow. The complex potential for a uniform flow with velocity u in the x direction is given by complex potential for a cylinder. To account for the presence of a cylinder of radius a, we use the method of images. The complex potential for the flow around a cylinder is. Here, the term \frac UA2az represents the effect of the cylinder on the flow. Streamlines and equipotential lines. The real part of Fz \phi xy represents the velocity potential, and the imaginary part \psi xy represents the stream function. The streamlines lines of constant \psi and equipotential lines of constant \phi can be plotted to visualize the flow. Visualization. For the flow around a cylinder, the streamlines can be visualized as follows. Streamlines, these are the paths followed by fluid particles. For the given complex potential, the streamlines are circles around the cylinder and lines parallel to the flow direction far from the cylinder. Equipotential lines. These lines are perpendicular to the streamlines and represent the potential function. Mathematical insight. Using complex numbers simplifies the mathematical treatment of the problem. Instead of solving partial differential equations directly, we can use the properties of complex functions to find solutions more easily. The Cauchy-Riemann equations ensure that the potential function and stream function satisfy the Laplace equation, which is a key requirement for potential flow. Conclusion. Complex numbers provide a powerful tool for analyzing fluid flow problems, especially in cases involving potential flow. They allow for elegant solutions and visualizations that would be more cumbersome using only real numbers. If you have any more questions or need further Sure. Let's go over the basic mathematical operations with complex numbers. A complex number is typically written in the form a plus b, where a and b are real numbers and I is the imaginary unit with the property that I squared equals -1. 1. Addition. To add two complex numbers, you simply add their real parts and their imaginary parts separately. Example. 2. Subtraction. Subtraction is similar to addition. Subtract the real parts and the imaginary parts separately. Example. 3. Multiplication. To multiply two complex numbers, use the distributive property and the fact that I squared equals -1. Since I squared equals -1, this simplifies to. Example. 4. Division. To divide two complex numbers, multiply the numerator and the denominator by the conjugate of the denominator. The conjugate of c plus d is cd. The denominator simplifies to c squared plus d squared because. So the division becomes. Example. 5. Conjugate. The conjugate of a complex number a plus b is a by. It is useful in various operations, especially in division. Example. The conjugate of 3 plus 4i is 3 4i. 6. Magnitude modulus asterisk asterisk. The magnitude of a complex number a plus b is given by. Example. The magnitude of 3 plus 4i is 7. Polar form. A complex number can also be represented in polar form as r \cosine \theta plus I \sine \theta, where r is the magnitude and \theta is the argument angle. Example. For 1 plus I. Magnitude r equals \s squared 1 squared plus 1 squared equals \s squared